So we have all of these laws that allow us to create new continuous functions from previously known continuous functions. Let's think about how we can use that. So let me just make up some examples here. So we know, for example, that x is continuous. If we multiply a continuous function by a constant, we have something that's continuous. If we also know, for example, that x squared is continuous. Multiplying that by a constant is continuous. We can add or subtract them to get something continuous. So this is continuous. We can multiply it by something else that is continuous. And this is also going to be continuous. And then we could divide this by something that is continuous, and this overall function is continuous. So note that I use, at various points, I use sum and difference rules, I use multiplying by a constant, I use product, I use quotient. So starting off with a small building block that constant functions and x to the n for positive integers is continuous, we have that this new function f of x is continuous. Now, the one thing we'd have to be careful about is the denominator defined. So this goes as long as the denominator is not equal to 0. So I rigged it x squared plus 1 isn't going to be 0 for any real values of x. And so we can do this more generally. The big punchline, so theorem 2 in this section says that P and Q be polynomials. Basically what I was doing was that I was constructing polynomials in the numerator and denominator. Then P is continuous on the entire real line, and P over Q is continuous on its domain, which is when Q is not equal to 0. So this previous set of laws provides us with a very, very powerful way to construct tons and tons and tons of new continuous functions. So now, imagine trying to figure out, it would be quite a mess to show that this function is continuous on the entire real line using the definition all the time. From the previous laws that we have, we get that for free. So that's very nice. Here I purposely had an example where the denominator is never equal to 0. If we have an example where the denominator is equal to 0, g of x is equal to x minus 3, x plus 2, all over x to the 7th minus 5x to the 5th, plus 37x cubed minus 2x plus 4. So polynomial up top, polynomial in the denominator. This is continuous at everywhere other than where the denominator is undefined. X is equal to 3, x is equal to minus 2. And so we have this very powerful way to construct new functions that are automatically continuous. Then at this point, we're just going to list off some more functions that are continuous. It's just some basic functions here. So y is x to the 1 over n, the nth root of a function. This is continuous on its domain. It might not always be defined. We're assuming here n is a natural number, a positive integer. Another thing that we know that are continuous, or we don't know, but the book tells us, is sine and cosine are continuous on the entire real line. a exponential function, y is equal to b to the x. B is a positive number that is not equal to 1, is continuous on the real line. So y is equal to 3 to the x. That's continuous. No more work to be done. And we talk about exponential functions. Well, guess what's coming up? We're going to have a log. So log base b of x is continuous, for x is positive. And we also want to restrict b is positive, b is not equal to 1. So here are some more functions that we just know are going to be continuous. Let's see, what else can we do with this? Sine x and cosine x are continuous, so we can combine those together to say that sine x over cosine x is continuous on its domain. And of course, what is sine x over cosine x? That's tangent x. Similarly, we also have cotangent x and secant x and cosecant x. Those are all continuous on their domain. So these are cotangent x is just cosine over sine, secant x is 1 over cosine. So we can use the previous laws to argue that these are all must be continuous. So, so that shows that there's lots of functions that we can conclude are continuous very, very quickly without much work.